Okay, let's start. Good morning. Welcome to the spring semester. This is Math 2270, 6th section, linear algebra. But perhaps it will be more accurate to call it linear algebra and geometry. My name is Alp. I'm a postdoc at the math department, my final semester here. I don't think this is something to as opposed to graduating, if you're a doctor, that means that they're not going to pay you anymore. So yeah.
Last semester getting paid.
Yeah. At least here. Maybe there are going to be better places in the future. Yeah. One has to be optimistic. I agree. In this economy. Okay. So today we're going to discuss some items from the syllabus, and if time permits, we're going to sort of start discussing a little bit math. I'm not going to. Okay, so let me first say this. The syllabus is on Canvas. I'm not going to distribute the physical copies. And whenever you see something written in red font, that means it's a link, which means that you can click it and like go to wherever it takes you. So ultimately, linear algebra is really one of the workhorses of all sciences, STEM in general, but some softer sciences also, because somehow we as humans like seeing lines. They're like orderly, and planes and all these kind of things, and they make us happy in some sense, comfortable. And the types of models that we end up using quite often are also linear to model things. And it turns out that even if the phenomena in real world or in wherever, in the world of computers, whatever, end up being not linear necessarily, we still want to use linear algebra. We like it so much. And that's sort of the starting point of calculus. This course is not going to be about that part. The calculus part is going to be about the algebra part. We're going to sort of start with systems of what we're going to call linear equations. And that really is going to be our bread and butter in this class. But also, we're going to start sort of coming up with certain narratives, certain ideas, and so on. And eventually, systems of equations are not going to be merely systems of equations. They're going to represent certain things and so on. And they're going to have their own sort of syntax. And I would suggest also beauty to them. Okay. So I'm not going to read the syllabus verbatim. I highly recommend that you go ahead and have a look at it on your own time. And maybe tomorrow, if you have any questions, we can sort of discuss them. I'll just go through the more important points. First, of course, expectations. One of the expectations is that I expect you to attend all lectures. On the one hand, I will be recording every lecture, and I'm going to be uploading one annotated video per week so that you can review things at your own pace. But simultaneously, I'm going to be taking attendance at random dates. Okay? So I'm expecting you to come to this class pretty much whenever it is available. What else? 10 problem sets, 3 in-class midterms, and 1 final exam. And so the problem sets and midterms are going to be basically per week. Okay? in this course, you're either going to have a problem set due Friday, whatever the Friday, or you're going to have a midterm. Okay, you're always going to have a, boss for the week, and that's all you're going to worry about per week. And we're going to have the cyclical nature. Okay. Okay. I'll let you read the learning objectives and all that stuff. I would presume it's important to questions. Questions? Okay. Grades are given like so. Attendance 5%. We have problem sets. That's worth 20. Better take this. Three midterms. First two are going to be worth 15 points of your final grade. Midterm 3 is 20 points, and a final 25. When it comes to later grades, it's standardized. All sections are.
Sorry, are there such like the homework problem?
Exactly, yes.
Oh, that's okay.
Yes.
Come up with this.
Yeah. Letter grades are standardized. I think it starts at 93%. That's an A, and then it sort of drops and so on. But there's some room to fudge around depending on how we go. Main textbook again is standardized. It's this textbook by Lay McDonald, Linear Algebra and its Applications. There's what is called this Day 1 Books Access Program, which means that if you didn't do anything, you already got charged for the textbook, and you already own it. And so if you go on Canvas, there's a tab called the bookshelf. And if you click on it, you'll have access to your copy, your digital copy. There are ways to opt out and get reimbursed as far as I'm concerned. But you should be, to figure out how to do that, you should check the link in the syllabus. Now, problem sets, I'm going to prepare by myself, even though I will take many of the problems from the textbook. So if it is the case that the only reason you're buying a textbook is so that you have access to problem sets, you don't need to. Okay, so they're going to be standalone, and you're going to have access to lectures as well. And on Canvas too, I added yet another sort of free set of lecture notes by Paul Dawkins. This is kind of like my favorite. That's sort of the set of lecture notes that I used back when I was taking this course many years ago. It's very to the point, okay? It's all about examples, because if you look at the textbook, some of you might like it, but you're going to see there's a bunch of lore and flavor text and blah blah blah. But when it comes to doing the homework or preparing for the exam, you really don't want to learn about the biography of this guy, right? If you're like me, it might be good to have a look at this set of lecture notes. What else? Well, I taught this class many times. Once before here at the University of Utah, and all lectures from that time, so like 2 years ago, lecture videos and materials are all available online, so you can. I really would rather you speak to me.
Sorry.
Yes. If you have a question, please speak to me. So you can follow the links listed on the syllabus to have a look at the previous material. I've listed topics in the tentative schedule on the syllabus. One thing I should mention perhaps is that we have a couple of rather more applied sounding topics. One of them is computer graphics. The other one is signal processing. And I believe the third one is dynamical systems together with nice things like PageRank. Now, last time I taught this class, I really emphasized these applications and I sort of de-emphasized the more mathy stuff. But then this semester, as I sort of discussed how to go about doing things, our coordinator suggested that I perhaps cut down on the applications a little bit. So that's why even though I wrote them down on the syllabus, it's kind of optional. So we're going to go to, for instance, when we reach week 8, that is reserved for signal processing, at least on the syllabus. And that's also not something that I'm coming up with, okay? It's in the textbook too. I'm not just like making these things up. So we're going to see, depending on how you guys feel about the previous topics and stuff, we might let go of these applications or we'll discuss some part of it and so on. So we'll sort of modulate as we go, okay? Any questions so far? Okay.
Sorry, teacher.
Yes?
Wasn't the exit credit?
No. I don't like inflation. Okay. Despite that, I should mention perhaps that I am rather lenient, especially when it comes to problem sets. And my aim is not to punish you, okay? As far as I'm concerned, grades are merely a tool to perhaps gamify the whole situation a little bit so that, you learn, you push yourself just a little bit more. One could argue maybe it's not very helpful, but that's not our job. Lectures, okay, like I said, I'm going to be recording every lecture. I'm typically recording myself, but should you sort of like pass through it, you don't need to worry because privacy is an important thing for me. Before I upload, I'm going to make sure that you're perfectly anonymized and everything. Okay, let you read the rest. Accessibility, inclusivity, and safety. These are important things, of course, but I'm going to let you read as well. All these matters. When it comes to AI, as part of academic honesty, and the general rule is that as long as it is reasonable, the way you're using it should be okay. I would probably suggest that you, in fact, perhaps get a little bit accustomed to LLMs. Presumably, by the time you graduate and you join the workforce or wherever you go, AI is going to be highly integrated in whatever you're doing, and you're going to be expected to be able to use AI. So I think I would be depriving you of, necessary or perhaps important experience if I had prohibited it. But of course, the point is to be responsible. And part of this course, I think, would be good to take as, well, it's a low stakes sandbox where you can experiment a little bit. Of course, I'm assuming that you're all taking this class in good faith, but things happen. We're gonna figure out the boundary, so to speak. One thing I should mention here, and there's a link on the syllabus about this as well. University of Utah recently made a contract with OpenAI, and as a University of Utah student, you have access to the latest models. You need to get access, whatever. So it might be good to at least get your access, and this is like all free. It's all included in your tuition and everything. Nothing extra, as far as I know. you might as well start using it a little bit. But of course, this is not to say that you have to be using ChatGPT to succeed in this class. Technically, this is a classical, old school class, pen and paper, whatever. Okay. So that's that. Okay. Any questions about anything so far? Yes.
Are the problem sets going to be turned in on paper or on Canvas?
On Gradescope. Yes. I thought about that, but yeah. Any other questions?
Is it on Gradescope?
You'll know. Don't worry. Yeah. Don't worry about it. There's a bunch of systems.
And the second question, when is our first problem set due? This Friday?
No. Let's do it next Friday. Yes. You're going to have 1 week per problem set. Okay. So the first problem set I'm going to upload on Canvas this Friday. Another question? Yeah.
I was just going to ask where to find the problems.
It's on Canvas. Everything on Canvas. So right now, if you go on Canvas, you're going to see under the assignment tabs, under the assignments tab, there's a bunch of like assignments, but they're all empty. As time goes by, I'm going to start uploading PDF files there. Okay.
If there's a day we know we're not going to be here, is there anything we should do other than just watch the lecture?
Probably you should let me know beforehand. Yeah, that's the thing. So I take attendance, but at random dates. So in principle, I'm expecting all of you to come to all classes. Okay, but life happens. And I'm going to be a lot more lenient when it comes to attendance as opposed to midterm. Right? So I have to take a flight, whatever. Maybe that's not that's not a valid excuse for a makeup for midterm, unless it's sort of like a school-related thing. You're representing the school at a competition, whatever. But for attendance purposes, certainly. There was another question somewhere over there. Okay. Office hours, I don't have specific office hours. Experience shows that it's better if you take the initiative, set up an appointment, meaning you send me an email, either you want to meet with me yourself or with multiple people. These are all fine. And then we come up with a time that is applicable, that works for all of us. Okay? Experience shows this works a lot better. Okay. Any other questions?
So for the problem sets, do you know if you have like a PDF like document we need to download, like a template that we should use to like write our answers or like complete the problems, or do we just do it on our own?
So the problem set, so for each problem set, there's going to be a problem set specification document. That's going to be a PDF file. So the statements of the problems, as well as how to submit, also some sort of like law or whatever, is going to be all in this problem set specification. But how you submit it back, it's going to be your choice.
But we're all using like the same template to do the homework, right?
There's not going to be any template.
Okay.
So, I mean, perhaps let me mention some of the things that I've seen other students do. Well, some of them, they just write on their tablets and sort of export it. Gradescope, this system that we're using, already sort of restricts the type of file that is allowed for you to submit. But other than that, it's all good. Okay. Some people, they write it old-fashioned way, and then they take scans, whatever. They take pictures with their phone, submit those. But that's pretty much it. Yeah. One thing I'm going to do is, for each problem set, I'm going to ask you to submit a Google form. This is, so I'm basically sort of, these forms are going to be essentially weekly feedbacks I'm going to be getting from you. how long it took you to finish this problem set, which problems were the hardest, which problems were, rather straightforward, whatever, and certain other comments. I'm a rather improvisational instructor, and I like sort of modulating the style depending on the audience. Okay. Any other comments or questions?
What's the policy for networks?
You're going to see it on the problem sets, and I write it, I think, on the syllabus as well. So if you go to the section for problem sets, which is section 9, the first paragraph, I think, is going to be sufficient. So basically, I allow 24 hours, and that's going to cost you 10% of the grade, and then after that, no grade. Okay, I'm rather strict about when to submit. Part of it is, discipline, whatever, but part of it also is that this is like a fast-paced course, and I would rather at some point, if you're missing things, that things sort of like carry over because you're going to be sort of like trying to catch up and so on. And problem sets are going to take you a long time. Okay, it's going to take the whole week. Okay. Was that satisfactory?
Nothing.
Okay. Any other questions or comments?
With that being said, how many hours should we expect per week to work on that?
I mean, as far as I'm concerned, so I'm going to make it so that it's around like 8 hours problem sets, 8 to 10 hours. But I think at least, especially for this course, we're going to start rather, mathy. Okay, we're going to be like, oh, solve for x, whatever. And then things are eventually going to get like scary all of a sudden. We're going to start using like words, span, whatever. And like, what is the dimension of this rank, all that stuff. And then there's going to be like definitions that I would presume is going to take a while to remember and stuff. I'm not sort of guessing what type of person you are. I'm just remembering how it was for me. Oh, there's the span, and then there's the basis, there's linear independence, and then there's the rank, and then there's the nullity, whatever. There's going to be like a bunch of things. And so the reason why I'm saying this is that when you're studying for this course, I'm going to make the problem sets, I'm going to prepare the problem sets so that you just prioritize doing the problems in the problem set, and insofar as you need to remember, you go back and like you try to remember or you try to understand the definitions. One of the biggest mistakes that students do in this course is they look at the textbook, notes, whatever, and they try to understand the definition. Okay? Paradoxically, that kind of doesn't work. In this course, if you try to prioritize being able to solve the problem or get the answer, whatever, starting from perhaps simple examples or trying to understand examples, it's going to work a lot better. As far as I'm concerned, that sort of seems to be sort of a valid strategy. Of course, you might be different, but from a lot of students, I hear things like, "Oh, I get the definition, but I cannot solve it. Like I cannot use it in the problem, whatever." Obviously, that is not good. So, and in the exams and stuff like that too, I'm not going to ask you what is the definition of this. Who cares what is the definition of that, right? You're going to need to know the definition to solve the problem, though, of course. Does this kind of make sense? Okay. Now, I should also mention I'm a pure mathematician, meaning I am oriented a certain way. I'm not really interested, at least in my training, how to use things, how to model things, and so on. I'm one of those people who do math for itself, but I'm also really interested in applications. And this course is typically taken by more users of math instead of pure mathematicians. And so hopefully we'll sort of find a middle ground. But if I start sounding a little too kooky, okay, I want you to let me know, okay? Any other comments or questions about anything here? Yes?
Will there be a formula sheet on the exam?
No.
Do we need to memorize it?
Yes. Presumably, instead of memorize, use the phrase learn by heart. But yeah. It'll be old school in terms of the midterms. But of course, suffice it to say, the exams themselves are going to be, I'm going to design them so that it's somewhat more applicable. Because the exams, the midterms are going to be like, you're going to have 50 minutes. And, you know, these rooms are not really optimized for exam taking. So I know all this stuff. I think about all of these things. And I hope in time I'll gain your trust as the statement that I know what I'm doing in a sense. Some people still disagree, but you know, to say the least, I do my best. Okay. Any other comments or questions?
Where will exams be taken?
In class, during class time. These are the midterms. The final exam, okay, it's going to be again in this room, but possibly at a different time. Look at the syllabus. That is governed by the university. They say, oh, if this class is taken, if this class is from this to this, meeting 4 times a week, you have to take the exam this time. So that is governed by university. But other than that, midterms are going to be in class. Okay. Any other comments or questions? That's a perfect question, and I believe the perfect answer would be to perhaps compare the previous materials available. Okay, go have a look. The problem sets, once you start getting the hang of it. I mean, I try to, okay, maybe I should say this as well. Typically, in any given problem set, there's a bunch of sort of relatively easy questions, but there's a bunch of like really hard questions also. Like some of the problems are going to be so hard that I'm not going to even expect all of you to, any of you to actually solve it completely. Okay, some of them are going to be hard like that. But obviously, those type of hard problems I cannot solve. I cannot ask you or give it in the midterm. It would be unfair in a sense. And so, when it comes to a midterm, a big part of the midterm is going to be made up of problems basically verbatim from problem sets. Okay, when it gets closer to the midterm, I'm going to probably share with you some sort of study guide, and I'm going to specifically list out certain problems. I'm going to say, especially make sure that you can do these problems in these problem sets. Okay, so a majority of the problems in the midterms are going to be things that you've already seen. There might be some sort of problems that are geared toward the top of the class in a sense, because we wouldn't want to be sort of victimizing them as well, right? But certainly, how to say? I grade things not to, punish people in a sense. Okay, that's always my aim, and I understand, especially midterms could be stressful and everything. All of these things, I'll be keeping in mind. But then again, people say one thing and do another thing. So you're going to have to wait and see. And then you let me know afterwards. And everyone else. Anything else? Okay. Just need to check when we stop. It's going to take me some time to get accustomed to the timing. We have about 20 minutes. Also, we might as well just start then. Maybe let's start with what we're going to end up at, where we're going to end up at. And this is one of the applications of linear algebra. Let's start like this. How many of you have heard of this thing called the Fibonacci numbers? Pretty much all of you. Very nice. What are these? Very good. Yes. Yeah, so it's a bunch of integers, right? You start at, some people start at 0, it doesn't matter. But the point is, to get the next number, there's a rule, right? The rule is, you look at the previous 2 entries in your list of numbers, you add them up, and that gives you the next Fibonacci number. So 1, and then you add 1 and 1, that's a 2, and then 1 plus 2 is 3, and so on. What is it, 13? Dot, dot, dot. Okay. And people say, you know, this is like important in architecture, all these things. Somehow it is related to this golden ratio or golden number, whatever. How many of you have heard of this number, golden number, or golden ratio? And what is this number? Do you know?
I remember it's like a rectangle and it makes like a spiral.
Yeah, but what is the value?
Oh, I don't know.
Isn't it like 1.6 something?
Okay, so you see this is where we differ. Instead of using decimals, me being a pure mathematician, I'd rather keep the radical, meaning the square root, so that I'm not sort of rounding off, whatever.
Isn't it like 1 point, it's 1 plus root 5 over 2 or
Yeah, yeah. So there's this number called golden ratio, or golden number, whatever, which is denoted by this letter. So this is, in this class, we're gonna use a bunch of Latin letters, but also Greek letters, okay? And so this is lowercase phi. Okay? This is the Greek analog of the letter F, okay? And so this is 1 plus root 5 divided by 2. And of course, just because I could validate your colleague's answer, that this is indeed the right number, that doesn't mean that I actually remembered this. Technically, or if I'm living, going about doing my business, the way I think about it is how your colleague over there suggested. Namely, there's a certain rule. And there's a reason why this is called the ratio. You have a rectangle. One side you call A, and the other side is longer. It's of the form A plus B. Okay? And so you say this sort of configuration fits into the golden ratio paradigm if the smaller rectangle is comparable, it's proportional to the larger rectangle. Okay, that's what it says. Meaning, this by this, right? A over B, longer over shorter, long over short. So A by B is the same thing as the long of the larger rectangle, A plus B, by A. Okay. And then you do a bunch of things, and it turns out that this essentially gives you this golden rule. It's not that important, golden ratio, how you actually get this. But somehow this is related to this. Namely, what you do is, well, you start with what do you call this? A square with each side of length 1, and you start adjoining to it a bunch of rectangles according to this rule. And so you sort of put another one here. That's a 1, that's a 1. And then you apply the same rule to this rectangle. You say, oh, one side is 1, the other side is 2. And so I should be adding a 2 here, 2 by 2 and so on. And if you keep adjoining more and more rectangles like this, it kind of generates the same sequence of numbers. Okay? And people in architecture, whatever, they really like this ratio for whatever reason. Well, how is this related to math? First of all, let me back down and let me try to make the sequence of numbers more relatable. Really, this, I mean, it's all good, but you know, it's just a bunch of numbers. Ultimately, there is, though, a reason why these numbers are called Fibonacci numbers, and that's because Fibonacci came up with this sequence when he was thinking about a certain rather simplistic model. How many of you have heard of this, perhaps? It's something about rabbits, how they sort of multiply. Okay.
Is he trying to find like an exponential, like an easy way to model it?
In a sense, but it's somewhat more specific, you see. So if you really don't care about these kind of things, and if you're more sort of, application oriented, you think of the following. And this is where it's going to be somewhat easier to come up with a connection between these numbers and linear algebra. Now, I call this a model, but it's a rather simplistic model, okay? There's a version of it that, in fact, Darwin used, but it's more complicated. You want to come up with some model about how bunnies or rabbits multiply. The point is that bunnies multiply rather fast. They reproduce rather fast. And so Fibonacci wanted to mathematize it a little bit. So the idea is this, okay? I'm going to denote, let's say, by a triangle, a pair of juvenile rabbits. And let's say by square, I'm going to denote one pair of adult rabbits. Okay. And now I have a bunch of rules. I say, well, if I start with a pair of juvenile rabbits, it's going to take them 1 time unit. I don't really care what that is, but throughout, it's going to be the same time unit. Maybe it's 1 day, 1 month, whatever. We're just going to fix it. That's going to be our time. So this is really the starting point of what is called discrete time dynamical systems. We're going to talk about this more all the way in week 15, the last week, or 14, whatever. if I start with a pair of juvenile rabbits, it's going to take me, or it's going to take them, 1 unit of time to mature. They're going to turn into adults. Okay? And juvenile rabbits, you say in your model, that's the difference between juvenile and adult, they don't get to reproduce. So if you have a pair of rabbits, you have to wait 1 turn until they start reproducing. So this is how I'm going to denote this. Okay, this is time progressing by 1 unit. Now they turned into adult. So this is time 1, let's say, this is time 2. Now the next time, at time 3, what happens is this. The pair of adult rabbits, they're going to survive. In my model, I don't want to think about when they die. So these rabbits are going to be immortal. And this is the difference, as far as I remember, between Darwin's thing and this model. Okay? But them being adults, in the next turn, they're also going to generate 1 pair of new juvenile rabbits. Okay? Does this make sense? I'm just like, there's no sort of right or wrong here. I'm just making up the model. I'm asking you if this, caricature kind of corresponds to what I'm actually saying out loud. Now what happens at time 4 then, you see, I have to apply the same rule to both of these pairs. This pair is going to survive, but it's going to generate yet another new pair of juvenile rabbits. They're infinitely fertile, okay? This is the model. But then, this pair of juvenile rabbits at time 4 are going to mature. Okay? Let's do one more. Time 5. Yes?
Shouldn't that middle one be a square?
Yes, thank you. Very good. Does this make sense? I hope at this stage you can imagine how this would sort of keep going like this. And it's quite fun, in fact, to start sort of doodling like this. And in fact, you can sort of come up with different rules for your model. Maybe you can sort of introduce, oh, they die after 5 times, whatever. These will be different sort of models. But the point here is that if you look at the number of pairs at each time, these also generate the Fibonacci numbers, you see. So I didn't write down 0, but 1, 1, 2, 3, 5, and so on. Does this make sense? Okay. Well, there is a linear algebra in this. Now we need to introduce some variables. Okay, I have been drawing some pictures and stuff like that, but not all of math can be done like this, at least efficiently. So this class is going to be all about not necessarily modeling things, but starting with the math itself. And this math is going to be the primary tool that you're going to use for many modeling purposes. And so let's say I denote by what do I need? J and A, let's say. J of n is going to be time, of course. J of n, let's say, represents or stands for the number of juvenile pairs at time n. Okay? Say number of juveniles at time n. Does this make sense? And likewise, A of n, let's say, stands for the number of adult rabbits at time n. And of course, what is the point? F of n, the nth Fibonacci number, is the sum of these. Okay. Okay. Now, when we first started talking about the Fibonacci numbers themselves, we had a relationship about these guys, f sub n's or f of n's. And what's the rule? Well, the rule is f of n equals f of n minus 1 plus f of n minus 2. Okay? But you see, somehow, instead of looking at an equation for f, it turns out, at least for our purposes, even though it is perhaps more cumbersome looking, it's better to think about an equation in terms of j and a. Okay? Why would I do this? Maybe I should ask you. If you've taken differential equations, maybe you see some similarity here. How many of you have taken differential equations? Not many of you. Okay. So there is also continuous time dynamical systems, and that's the world of differential equations, at least for now. So we're not going to get into that, but there's something very similar happening here, really. In a sense, the reason, one of the main reasons why this perhaps is not very good is to figure out what happens at time n, you have to go two steps back. So now what you want to say is, well, let me introduce more variables. I'm going to use more variables, but I want to go back in time fewer times. Okay? So I want to relate j of n and a of n to j of n minus 1 and a of n minus 1, and I don't want to look at what happens at time n minus 2. Okay? So if you want, from a computer science perspective, you're trading the time complexity, something complicated in terms of time, to something complicated in terms of space. If you know what this means, that's good. If you don't know what this means, it doesn't matter. Okay. Okay. Now, how can I write these two in terms of j of n minus 1 and a of n minus 1?
For like the juvenile rabbits, it's just going to be the same as the amount of adult rabbits there were in the previous generation.
Right? Because how could a pair of rabbit be juvenile at time n? That means that there was exactly one adult pair in the previous time that contributed exactly those pairs. Does this make sense? And then at this point, you may be sort of inclined to say, well, if j of n is equal to a of n, what's the point? Okay, this is going to be important for us in this class. We're going to sort of introduce multiple variables, but sometimes they're going to be equal. Doesn't matter. Yeah.
But it's equal to a of n minus 1, right?
Yes. Thank you. In this case, because of that, I guess it does matter. But then again, there is some sort of redundancy, you could say, right? So why do I need this new variable with a time shift? This is going to be important for us. I don't want to keep pushing. We're out of time. But we're going to keep talking about this tomorrow. Thank you. All right. Let's start. Good morning. So today we're going to talk a little bit more about this Fibonacci stuff. don't worry, this is not the main thing that we're going to deal with for quite a while, or maybe you should worry because that's what's going to happen. It's going to turn into more sort of abstract, mathy type of stuff. This is really the type of stuff that we're going to deal with at the end of this course in week 14. So we're going to sort of pick up a bunch of like tools to really discuss what is going on. I'm just going to mention a couple of factoids and some things that might sound like magic or, you know, these like cheap tricks, but there's like some deep stuff underneath. And then after talking about this just a little bit more so that you have some, you know, some motivation as to why to study linear algebra and things like this, we're going to really switch over to what we're supposed to cover this week, which is systems of linear equations. And we're going to start talking about matrices and stuff like that too. Before I go into that though, I had suggested that maybe you have a look at the syllabus on your own just a little bit and see if you have any issues or questions or comments about anything that's on the syllabus. Okay. So I'm going to keep asking this throughout the week. Some of those of you who were here yesterday probably see some new faces. Just to give an explanation, I think there were one more section of linear algebra, and they canceled that because of low enrollment. And so now there are fewer sections and they all have wait lists. And some of your colleagues that are amongst you are really coming from this other section. So that's what's happened, as far as I know. It's not something that I had any say, obviously, but it's a reality of life. And so I'm not going to go over the syllabus again. I would suggest if you're one of those newer students in this course, maybe talk to someone who was here yesterday. And certainly you have access to the syllabus on Canvas, which you should have been enrolled already automatically. If you're not enrolled on Canvas, just send me an email. Maybe I should write my email then. And I'll add you manually. Usman@math.utah.edu. Okay. So what we were talking about was this Fibonacci numbers business. Initially, we sort of looked at this sequence of integers. Okay. The rule is, well, you start with any two really. It doesn't really matter that much. These are, what would be called seeds or initial conditions. But the real thing is the time evolution. In other words, how do you get the next term? This is what is also called a recurrence relation. And the idea is to get the next term, you look at the previous two terms and you add them up. Okay? So this plus this is this plus this is this plus this is this, and so on. Now, in principle, you could also run the same thing backwards. There's nothing stopping you from doing this. You could say, what is the term here such that if I were to add this term to 0, I get 1. So for instance, you will get -1 there. You could run the simulation in negative time as well. But let's not worry about that. That was the first thing that we discussed. And then I said, oh, there's something called the golden ratio, which remember is denoted by this Greek letter, lowercase phi. It's a certain number. And indeed, it has the specific value, 1 plus root 5 divided by 2. And how do you remember this? Not that it's very important for us, but still it's general factoids. You look at a rectangle like this that has a smaller rectangle. One side is shorter, the other side is longer. You say this side is A, and the residue, let's say, of the longer side to the shorter side is b. And you say that this rectangle is proportional corresponding or according to golden ratio if the larger rectangle is a scaled copy and also rotated copy of the smaller rectangle. Okay? And so phi is long over short, this ratio. It's not the numbers themselves, but their ratio. That's why it's called the ratio. And so you look at the smaller rectangle. For the smaller rectangle, the longer side is A, and the shorter side is B. So long over short, coming from the smaller rectangle, is A over B. But on the other hand, from the larger rectangle, if I look at long over short again, I get A plus B over A. I set these equal to each other, and somehow, if you solve this, you get this value. Okay. Now, what does it mean to solve this equation to get this? Now, this course is linear algebra. It's about linear algebra. But we will be using a lot of the math that hopefully you have learned before. And some of this math that you've learned before is not necessarily linear. So any guesses as to how to start from this and get this guy? In other words, I'm asking about this equality. How do you compute this number from this? Any guesses or ideas?
Choose a random value for A and then solve for B.
Yeah, you could do that. But then how do you know that what you computed doesn't depend on A? But I guess what you're saying is this. Pretend that A is a fixed value and then solve for B. Okay, how do you solve for B?
Algebraically.
What does that mean? There's a formula here ultimately.
System of equations?
It is a system of equations indeed, but you know. I want something, it's like something formula.
Would it be like an induction formula or something like that?
The quadratic formula?
It's as simple as this. Quadratic formula. Do we remember this?
Yeah.
B squared over whatever, all that stuff. With the square root and everything. Somehow this square root is that square root actually. So what does this mean then? Just to reiterate, well, you sort of like cross multiply and all that. Let me write it here. This looks like, it sounds like maybe it's not relevant, but we're going to keep using this quadratic formula quite a bit in this course. Okay. So I'll record it here. What was it? A. So this by this is the same thing as this by this, right? Because I don't want to see divisions. Okay. A squared, let's say, minus 2ab minus b squared equals 0. Does this make sense? I just got rid of the divisions and then collected all the terms on one side. How do I apply the quadratic formula here? Well, I'm going to use exactly what your colleague suggests. Even though everything is just a letter here, you can say, well, I'll just pretend that A is a fixed number and solve for B. You could also do it the other way around. It's going to give you the same value. So fix A, solve for B. Of course, you can, there's no 2 here. Of course, you can complete to a perfect square, whatever. There's a bunch of methods to solving this. I hope you've seen some of these ideas. But somehow, you solve it for B. Say, using the quadratic formula. Okay, I'm not going to tell you what the quadratic formula is. If you're able to enroll in this course, I guarantee you, even though perhaps you don't remember the formula itself, you've seen this at least in some other course before. If you don't remember it, and that is perfectly fine, because based on experience, I know that some of you have done math maybe like 2-3 years ago, last time, don't quite remember. If you're one of those people, and even if you're not one of those people and you don't quite remember, I urge you to go online, Wikipedia, whatever, and remember how to use this formula. Okay? So that's an exercise. So I'm going to keep throughout the course during class, I'm going to give a bunch of exercises like this. And I'm going to explicitly state that these are exercises. And when I say this is an exercise, that means that you don't need to turn in anything, okay? That's for you to talk about and so on, or think about, compute on your own. It could happen that I give an exercise in the class, and then in the problem set 2, you see something very similar, maybe an expanded version of the same problem, essentially. But the point is, if I give an exercise in the class, that means that it's something for you to study, and there's nothing to turn in. Okay. Any comments or questions so far? So what we were dealing with was not quite this, but rather a more perhaps biological or ecological, let's say, interpretation of these numbers, Fibonacci numbers. And we said, oh, we have these juvenile rabbits and then the adult rabbits, and then we have this model that basically goes like this. You start with one pair of juvenile rabbits, which really, let's make this connection as well, corresponds to this stage. Okay. And then we sort of start what we said our dynamical system, and it's a discrete time dynamical system. So time progresses in discrete time steps. I don't quite specify at this stage because this is not a super realistic model anyway. And so in the next time step, this juvenile pair turned into an adult pair, and then going forward, any adult pair generates a new juvenile pair, and it survives also. And this is supposed to sort of justify why rabbits reproduce rather quickly. Okay, so it keeps going on like this. For instance, this then turns into this, and then this, and then this turns into this, and so on. Okay, I'm not going to draw this again. What we were trying to do was, instead of looking at the Fibonacci numbers themselves, we were trying to rewrite the same relationship, or something that is equivalent to the relationship that we wrote, in terms of J and A. You see, this J and A were the new variables that we've introduced, corresponding to the numbers of juvenile pairs at time n and adult pairs at time n. Okay, so this is also, of course, f of n is the sum of them, we said. So nth Fibonacci number. Okay. And so this is perhaps one way of justifying why you would even look at these numbers. And of course, I'm not claiming anything about the validity of this model. It's clear that this is not very accurate. First of all, there is no sort of limit. The population is going to go to infinity, for instance. And one of your colleagues yesterday suggested, in fact, this population is going to blow up exponentially fast. Certainly, this cannot be real. But then, if your model is, so if that happens, if your model doesn't quite match with reality, there are things you can do. One of them is, making it, in a sense, more complicated. You would say, oh, my rabbits are not immortal. This model really requires that the rabbits are immortal. But you could also assume that they are not immortal, in fact. They die at least, let's say, after 5 steps. You could add some randomness, whatever. But as you can imagine, if you want your models to be more accurate, then the models themselves are going to be more complicated, which means that you need to know more math. And I don't want to go there. And so the rule was this. In terms of the Fibonacci numbers, f of n equals f of n minus 1 plus f of n minus 2. And we said, instead of using multiple times like this, so in order to figure out what is happening at time n, I don't want to go 2 steps back. I want to go 1 step back. But I want to use more variables. That's what we said yesterday. And we were trying to come up with a, what we're going to call system of equations that really involve these 2 variables. And that's where we finished last time. So we're going to continue from there. Just to reiterate, first of all, we realized, or one of your colleagues suggested accurately, that the number of juvenile rabbits at time n is exactly the number of adult rabbits at time n minus 1. Right? Because the only way at time n you see a pair of juvenile rabbits is there's a unique pair of adult rabbits in the previous time step. In other words, you have this. Does this make sense?
In this sequence, at the very beginning, we only have 1 juvenile, but no adults.
Yes.
How does that work out with that equation?
Well, you would probably quantify n. You would say something like j of 0 is 1. So you would say this really works for n at least 1 or something. Yeah, I'm sort of being vague there, but you're right, of course. Any other questions about this? Question? Okay. Now the perhaps harder thing to figure out is a of n. I want to come up with a formula for a of n. Again, in terms of a of n minus 1 and j of n minus 1. So let's think about this now. Any guesses as to what this should be? I want something here.
A of n minus 1 plus j of n minus 1.
Okay, your colleague suggests this. Can you perhaps say a couple words about why this should be the formula?
Because the number of adult rabbits is the number of adult rabbits in the previous one, because they stay alive, plus all the juvenile rabbits will turn to adult rabbits.
Exactly. Does this make sense? So that's the word problem version, but when you turn it into math, that's how you would write it. Okay? Any comments or questions about this? Yeah.
Yeah, so I originally thought you could take a step forward instead of a step back. So why would you need I get why the j of n is there, but why would you need the j of n minus 1 there? Or the a of n minus 1. I get the first part, but why that second part?
Oh, okay. So I guess the point is this. When I write something like this, I'm really saying, so this is, in a sense, an algorithm as to how to compute what happens at time n, assuming that you know what is happening at time n minus 1.
So, because theoretically, like a of n could equal j of n plus 1, but we can't really go forward. So I was gonna say, why would we take a step
A of
back?
n could be equal to j of n plus 1?
Yeah.
Okay, you can do something like this, of course, but that doesn't quite match with the model that I described. The point here is that I'm sort of like fast forwarding this, but yesterday I gave a certain model, which in terms of the Fibonacci numbers, in other words, the sum of j and a, it was this. So I'm saying, oh, okay, whatever, this is my model now. And I'm trying to rewrite this in terms of this. So I'm trying to rewrite an equation for f as a system of equations for j and a. Okay.
Does it matter which one is j and n and a of n up there? Because you said f of n equals j of n plus a of n. So it doesn't
Yes.
matter which one is equal to like.
Of course, you could denote by j number of adult pairs and by a number of juvenile pairs, but then why not use uppercase letters that correspond to what it stands for? You could, yes. Theoretically, it doesn't matter. You're right. Yes.
Wouldn't like an equation using n plus 1 only work if you have knowledge of every step already? Because this one, you could start from just your first day and then keep going. But if you have one that references a day ahead, you could never solve it.
Okay. So you're right, of course. The point here is that in the Fibonacci numbers, and even in this drawing I put over here, I did start with a seed. But when I'm writing these down, I'm not saying anything about where you start at. So if many of you haven't taken differential equations, but comparing this to differential equations, this would be the differential equations part, and then there would also be initial conditions. So this is not quite something you can solve to get these numbers. You're right. So you would say something like, if you want to be more specific, okay, let's be more accurate. For n at least 2, f of 1 is 1, f of 0 is 0. Okay, so now I included the initial condition, or the seeds, and I'm saying this equation actually only holds for n at least 2. Does this kind of make sense? This is how you would sort of be more accurate about these kind of things. You would want to quantify the time parameter and so on. And here too, you would say for let's say n at least 1, and then you would say j of 0, well, maybe we should have started at 1, so let's say this. J of 1 is 1, a of 1 is 0. Go ahead.
So that basically means that at time 1 there's only one juvenile and no adults, right?
Yeah, exactly. Yeah, so these time parameters and stuff like that, these get more technical. These are the types of things that you end up needing to worry about if you're trying to use these kind of things. But any other comments or questions about these?
So could we rewrite this bottom row as a of n is equal to f of n minus 1? Or is that working backwards?
Say again?
So could we say that a of n is equal to f of n minus 1?
You could. Very good. Your colleague is suggesting, instead of writing it like this, why not just write f of n minus 1 here? Because ultimately, f of n equals this. But the point here is that I want to get rid of f altogether. because somehow this format is what we're going to focus on. This exact same thing we're going to write using a matrix, okay? And using a matrix, we're going to write it like so. I'll do it here. Because you say, even though in principle, J and A are independent variables, and they are related precisely in this way, you want to think of them as one thing. That's why this is called the dynamical system. Okay? So what you do is, you have these two numbers. Well, we're going to store both of them in one array. It's an array of numbers. And the way we're going to write it is, we're going to come up with a 2-by-1 array. That is to say, we're going to store J of n and A of n on the left-hand side into one thing. So this is what we're going to call a 2-by-1 matrix. Then we're going to have something here. And in a similar fashion, just like this 2-by-1 represents the state of the system at time n, we're going to come up with yet another 2-by-1 that represents the state of the system at time n minus 1. And finally, here, we're going to have yet another array that's going to represent, ultimately, this right-hand side. We're going to talk about how to do this probably in a second, but let me just say, this is going to be now a 2-by-2 matrix, okay? And this turns into this. 0, 1 here, and then 1, 1 here. Okay. Don't worry about how I did this conversion. I'll mention it in a second. We're really going to sort of focus on this conversion to begin with for the rest of this class. Let me mention this. Somehow it might sound like, or it might seem like, I started with something simplistic, and I'm sort of making it more and more complicated. I'm introducing more variables, and now I'm sort of writing this in this bizarre fashion. Okay? While that might be true, in this case, part of the reason why everything is nice here, and you might not be able to see why one would need this in this case, is because the relations here are rather simplistic. You have two variables, and so on. But as a user of linear algebra, typically the systems that you're going to deal with are going to have many variables. Okay? So somehow you want to come up with a method of writing down systems of linear equations, we're going to say, that scales rather straightforwardly. So we're going to see this style scales rather nicely if you have more variables. Okay? So in a sense, the algebra part of linear algebra of this class is not anything new. It's all about writing a bunch of equations in a consistent manner that has nice logistics. Okay, we're going to see what this means in a second. Yet another thing that ends up being very important for our case is that somehow, once you get to this matrix form, we're going to say, well, the thing that drives the system really is this 2-by-2. So these four numbers put in this configuration. Okay? And somehow, being able to think of these 4 numbers, which ultimately, came from this, came from a bunch of places, being able to think of these 4 numbers as one thing, okay, this specific, if you want, data structure, ends up being very useful. We're going to say, for instance, this is the matrix that drives the system. It's the propagation matrix, or propagator. One of the things, for instance, that you might be interested in the situation is trying to answer the question of, well, what is the 57th Fibonacci number? Okay? Right, so you start here, okay, 0, 1, 2, 3, whatever. You would keep counting it. In principle, to compute the 57th Fibonacci number, you would need to keep adding terms until you reach 57 in time. Right? But that's not quite efficient, because that means that to figure out the nth Fibonacci number, you would need to add at least n terms. More than n, actually, but never mind. On the other hand, if you can really understand the system, this 2 by 2 that drives the system, it turns out that to compute the 57th Fibonacci number, all you need to do is to compute the 57th power of this 2 by 2. What does that mean? Well, we're going to get there later. So somehow these matrices, things like this, is going to be for us higher dimensional numbers. Okay? We're going to learn how to add, multiply, take powers of matrices like this throughout this course. Okay? And then later on, we're going to, for instance, start using phrases like, eigenvalues. Okay? This is going to be one of the most important concepts in this course. Turns out that this number also is the top eigenvalue of this specific matrix. Okay? So these are all things that we're going to learn throughout the course. I just wanted to mention a couple of these ideas, just so that you have some inkling as to where we're going. Now, most of the course, we're not going to be dealing with rabbits or modeling things, whatever. You might see some problems in problem sets, but in principle, we're just going to have equations that you might have seen before, and we're going to try to solve for x, y, z, whatever. Okay? Any comments or questions about any of this so far?
I have a question.
Yeah.
Can you offer like a very simple definition of the eigennumber?
I can, yes. Yes. I mean, so I guess it depends whether or not it is simple, because I could use a couple different other phrases.
Yeah, I understand. Yeah, you just mentioned it briefly, and I didn't really grasp any of the conceptual things.
Oh, I see.
Like you wanted to communicate a little bit.
Oh, yeah. Don't worry about it. You can just take the word eigenvalue as like a buzzword for now. Okay? It's something. Okay? It's an important thing. Yeah, we're going to talk about a very important theorem later. I'll tell you more buzzwords. It's called spectral theorem. Okay? So somehow this ends up being related to physics. So they say, there are different light sources and stuff, and these light sources have different spectra, they say. So you look at it through a prism, and some of them split into different colors. So somehow eigenvalues are one of these different colors. But for math, for purely abstract reasons, okay? We're going to learn all about this. It's one of the crown jewels of math as far as I'm concerned. Does this kind of make sense? Maybe it does. It makes less sense. If you're more adjusted to physical stuff, eigenvalues end up corresponding to energy levels that are admissible to whatever operator you have and stuff. But don't worry about any of this, okay? For quite a while, we're not going to talk about eigenvalues, eigenvectors, all that stuff. But we'll get there, okay? It's one of the important parts of this course. What I want to rather start with is the notion of a system of linear equations. Well, these are pretty much things like ax plus by equals c, okay? We're going to have a bunch of numbers and a bunch of unknowns, and we're going to try to solve for the unknowns. That's how we start with. And even before giving you the general form, I'd rather give an example of a system of linear equations. So for instance, here's an example. Read it. So now we're in the regular track, and if you look at, I'll make a comment about this too. If you look at the syllabus, there's a tentative schedule there. Week by week, I listed down what we're going to cover and so on. And for each week too, I have listed a bunch of sections from the textbook. So this course is a second year course, and I'm going to follow the textbook rather closely. Some of you are taking an advanced course for me right now as well, and that course is somewhat different. But this course, I'm going to stick to the script. So, systems of linear equations. Typically what I'm going to do throughout is, instead of giving first a definition, I'm first going to give possibly a bunch of examples. And then I might even skip giving the definition itself. Because often, as far as I'm concerned, giving the definition at this level ends up being rather confusing. So you're going to see, if you start reading the textbook, there's something called an echelon form, and you sort of keep reading it and kind of doesn't make sense almost. But, you see an example, as far as I'm concerned, it makes a lot more sense. So here's an example, okay? X1 minus 2x2 equals minus 1, minus x1 plus 3x2 equals 3. That's an example of a system of linear equations. How many of you have seen something like this before? Maybe, okay, pretty much all of you. Maybe you haven't called this a system of linear equations, but this is what we're going to call it. Maybe some of you have seen, instead of x1, just x, and instead of x2, just y. But of course, this doesn't matter. These are dummy variables. And I could have written it like this as well. But maybe I should mention this. This already signifies that we want our notation to, we want to be able to scale the notation. Of course, we have 2 variables. It doesn't really matter that much. But when you have 55 variables, 10 billion variables, whatever, which ultimately is what things like LLMs require underneath, you need to come up with some sort of indexing mechanism. Many of you are taking, many of you are computer science majors or computer science adjacent majors, and this is rather familiar to you as far as I know, but this is going to be part of the business for us. So this is what is called a system of linear equations. Why do I call it a system of linear equations? Well, because by definition, a system is something that stands together, okay? Even though these are separate things and I can think of them separately, and probably you've seen, oh, this is just the equation of a line and I can draw it and all that stuff, right? Rather, you want to think of this whole thing as one thing. Okay, that's why you call it a system of linear equations. In this case, for instance, we're going to say that this is a system of linear equations with two unknowns, and it consists of two equations. Maybe I should have restructured the sentence. So what I'm trying to say is this. If you have a system like this, we're going to have two integers that are very important, that you can always associate. One of them is the number of equations. In this case, there are two. The other one is number of unknowns. x1 and x2 here are the unknowns. Okay? These two are the two important integers that we're going to associate to each system of equations. It's going to be important to eyeball certain things later on. Okay? This is somewhat obvious, but I think it's important enough to keep repeating. So let me write these down. When I write this, obviously the point is to solve for x1 and x2. Okay. I'm sure those of you who have seen this before know how to solve it as well, but let's not worry about it for now. I want to introduce, okay, first let me remind you this, or let me record this. Two important integers. Number of equations and number of variables, okay? Number of equations, number of unknowns, perhaps I should say. It's going to help you throughout this course if you make it almost a reflex to record these numbers the moment you see an equation, a system of equations like this. Okay. Later on, these are going to have specific names. One really corresponds to what we're going to say, the dimension of the output space. And this, number two, is going to correspond to the dimension of the input space. Why do I call this input and output? Why am I using this terminology? Well, it turns out that many things that we're going to look into in linear algebra in this course, even though it doesn't seem like it on the outset, it turns out that it's rather useful to think of these things, matrices, whatever, as input-output relations. This is going to make more sense later. Don't worry about it for now, what these phrases mean and everything. Any questions so far? Okay. I want to introduce two more things. Let me just check the time. Before solving this system. Okay. We have about 5 minutes. I'd rather introduce the notions. One of them is what is called the matrix form. I did that with Fibonacci. I'm going to do the same thing here. Okay. So you have the left-hand side and the right-hand side. You have two numbers like this. So you store them into 1, 2 by 1. If you want, you can sort of write down this array like this, typically this is the notation you would see. In the textbook, instead of parentheses like this, you would see square brackets. I like this more. It's faster to draw and stuff like that. So I'm going to often use this notation, but these are all the same thing. Okay. If you like this, you can use this as well. Or this, of course. So this is the right-hand side. Two numbers on the right-hand side I stored into one higher dimensional number, 1 2x1 matrix. Equals, now I have something on the left-hand side. The unknowns I'm going to store into one variable, one matrix, like so. Okay. And just like in the case for Fibonacci, I'm going to have a 2x2 here. Don't worry now why this is how we do it, but ultimately, this is the pattern. I look at the coefficients, okay? 1, minus 2, minus 1, 3. I literally record these in this position, in the same position. You have to be careful about where you're recording things, okay? You cannot just record whatever number you see in wherever spot you see. There is a certain flexibility that we're going to discuss later, but for now, just write it like so. Okay? So this, you see, we're going to call the matrix form of the system. Or we could also call this a vector equation. So you see, this is like ax equals b, and solve for x. Except that a is not a number, x is not a number, and b is not a number. They're like higher dimensional numbers. So this is what we're going to call the matrix form. Okay? Does this make sense so far? I'm not doing much math here. As you see, I'm just rearranging things. It's surprising how much sort of structure there is in, writing things in matrix form. I need one more thing. This is what is called the augmented matrix form. What you do is you even get rid of these variables. You say, I'm going to forget them. I'm going to not write them down. I don't really care because they are dummy variables, whatever. You say, what really matters are these 6 numbers. So you put them in one matrix, but you want to use some notation that signifies, oh, one side is the left-hand side and the other side is the right-hand side. And so because of this, you write it like so. Now you start a 2x3. Maybe I should not put the bars here, because that's going to be confusing. You put 1 bar. Here, you record the right-hand side. And here, you record the left-hand side. Okay? So you just recorded all the numbers associated to the original system of equations in a consistent manner for now, let's say. This is what we're going to call the augmented matrix form, or augmented matrix. Okay. Okay. We have some more business to do with this example. I actually want to solve it to come up with the numbers and stuff like that. We're going to continue doing that tomorrow. Thank you. Okay, let's start. Good morning. Not many people answer actually, but any comments or questions about the syllabus? Okay. I received some questions about the textbook. Again, to reiterate, if you didn't do anything about the textbook, that means that you got charged and you already own a copy. And how do you access it? You go to Canvas for our course. And there's a tab that says Bookshelf. And you click that, and there takes you to some other system, and there you have access to it. Okay? But it's not technically mandatory to by the book or whatever. And there are certain procedures that you can try going through if you are not that interested in owning. But certainly it would be helpful. Okay, another thing I want to say is now today we're going to really start switching over, doing actual math, calculate things. And the nature of calculations in linear algebra is, well, we're going to start with something and we're going to keep writing pretty much the same thing. Okay? And we're going to be like very systematic. And I'd rather not keep erasing what I'm writing. So I'm going to start writing things in smaller font. So if you're having issues with reading things, if you're like me, I would suggest that you come forward and sit somewhere in the front. Okay? Now, we were discussing this system of equations. Okay? We started with this. I said whenever you see something like this, a system of equations, two things you want to look at first. One of them is how many unknowns are there. In this case, 2. And how many equations there are? Again, 2. In this case, these two numbers are the same. So that's the good case in a sense. But this doesn't need to be the same. Okay? You could see 10 equations with 5 unknowns. Or 10 equations with 20 unknowns. That can happen. We said there are 2 associated ways of writing the same thing. One of them was this matrix form. Okay? And what is this point? The point is this, okay? Instead of seeing a bunch of numbers that are sort of separated, you say, oh, I have the right-hand side. I'm going to put that in 1. We said matrix. And again, I want to think of this whole thing as one thing. One thing that contains 2 pieces of numbers, okay? Two numbers. And I have the equality. And on the right-hand side, what was the point? x1 and x2, I want to combine into one matrix. And I'm going to write it like so. So you see now this is my unknown matrix. Really, I'm trying to solve for this specific matrix. And then I need to store the remaining coefficients. And I just store them the way I see them. Okay? I don't get to just move them around. This is very important for us. So 1 minus 2 minus 1, 3. So now this is a 2 by 2 matrix. Okay, that's what we said. This is the matrix form of this system of equations. This is literally the same thing as this. Okay? I introduced one more way of writing things. You go one step further and you even erase, you get rid of this x1 and x2. And the only thing you end up recording are the coefficients, are the numbers. Okay. So how do you get from here to there? You get rid of the unknown matrix and you sort of combine both the left-hand side and the right-hand side. I like to put a bar here just so that I'm not confused. In the textbook, they don't do this. And whenever I say I do it this way and stuff like that, don't take it as me saying you have to do it this way as well. Okay? So many of you come from different disciplines, and chances are in your native major, the notation is different. Okay? I'm going to try to stick to the notation in the textbook as much as possible, but I have some idiosyncrasies. I'm going to try to be vigilant and let you know when that is happening. Okay? Any questions so far? We had done this before yesterday. I just wanted to reiterate. Now, here's the definition. Okay? Now I'm defining a general m by n matrix. Okay? You call it some letter. Typically, we're going to call sort of like a rectangular array, like so, uppercase letters. That is not necessarily, the rule. And so, just like with variables here, we used some indexing, 1 and 2. In the case of an m by n matrix, Well, we're going to need two indices. Okay? One index for m, another index for n. And so I have, again, you see, a table or an array of numbers to begin with, but it could be pretty much anything you want, really. And how do I index this? What is the rule? In each row, you see, the first index is fixed. So here's the first row. The first index I see is always 1. Okay? In the second row, the first index I see is 2. And I have a total of m rows. Okay? On the other hand, in each column, I have the second index fixed. You see, this is the first column, and the second index is always 1. And in total, I have n columns. So whenever I say A is an m by n matrix, you should imagine an array that has m rows, n columns. That's always going to be the case. In any fields, whenever you see linear algebra, this is how people use this. This is number of rows, n, the second number, is the number of columns. We're going to need to keep track of these numbers eventually. Those of you who are doing computer science, maybe you could imagine this something like this. So we're going to have blah, 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 and then we have an m by n matrix. Whenever I think about, for instance, a 2 by 3 matrix, I'm always going to sort of, I'm almost going to allocate some memory. Okay, I'm going to say 2 by 3 matrix. Okay, I need a 2 by 3 matrix. I'm going to sort of reserve a certain space. Then I'm going to start doing calculations and start filling in these blanks. Okay? We'll see what this means later. These two numbers are very important. Okay? And just because these are very important, sometimes I want to denote these numbers near this letter A that represents the whole thing. And whenever I try to do that, I'm going to use subscripts for A itself. Okay? And I'm going to write it like so. I will write A, M, the first number, that is the number of rows. I'm going to write here. So it's a subscript, but to the left, and subscript, but to the right. Okay? This is the way I write it. Hopefully this is going to make sense when we start talking about multiplying matrices. There's going to be a certain condition of compatibility for us to be able to multiply matrices, and recording these numbers, m and n, is going to be very helpful. Okay, this notation is so that that matrix multiplication becomes more automatic. We're going to see that later. Now, I'm not going to do this myself. I'm going to give you as an exercise. Just like I came up with this matrix form corresponding to this linear, I guess I should define the linear system first. So here's the linear system of equations in general. A11 multiplied by x1. A1n multiplied by xn, and I'm adding all of these up. This is my first equation, and I'm saying, okay, so on the right-hand side, I'm seeing some other variable or known number, b1. And I go like this, and I have a m1 x1 plus, so this is a product, plus a mn xn equals bm. So this is the general definition of a system of linear equations. Okay? Yeah.
Does every equation have to have the same number of unknowns?
Yes. But in principle, of course, you could see, so in principle, some of these coefficients, we're going to say, could be 0. In that case, maybe in some of the equations, you don't see every single unknown explicitly. And when you see this, the idea, of course, at least in the beginning, that they gave you aij's, these are known numbers, and they gave you bi's, and the point of this is to solve for xj's. Okay? Given aij's and bi's, solve for xi's. Okay? That's the general definition. I'm going to leave it to you to transform that into the matrix form. Okay? I hope you would agree with me. You should be using this matrix in the matrix form of this. Does this make sense? Because you see, there what we did was we saw all of these coefficients. We didn't move them around. I just abstracted out the coefficients and put them in the matrix. Here too, the coefficients here, the way I wrote them, matches with this. You have to again store the unknowns, x1, x2, whatever, into one matrix like so. And you're going to have equality. On the right-hand side, you're going to have bi's. Okay? Write this down slowly. And similarly, write down the augmented matrix form. Write down the matrix form and augmented matrix form, or augmented matrix. By the way, I should mention 99% of the time in this class, we're going to need at most 2 indices. But for sciences, that's typically not enough. There are things that require 3 indices, 4 indices, many indices. So these are what are called tensors. Okay? If you end up doing physics and stuff like that, you're going to learn how to manage more than 2 indices. But in this class, we're not going to really need that. It's somewhat more advanced. Okay. Any comments or questions about this so far? So ultimately, this is still nothing but just management. I'm just telling you, oh, write it like this and write it like this and so on. I'm not doing much math. But now I want to start doing math. And I want to start by solving this equation. Now, those of you who have seen something like this before probably know how to solve it as well. But I'm going to try to suggest to you to use a certain method. If you like, question? If you're like me, your reflex is to perhaps choose one of these equations, solve that equation for one of the variables. Let's say you take the first one, you solve it for x1 by saying, let's just do this perhaps. Method 1. Now I'm continuing with the example. Take the first equation, and in fact, let's do this. Let me enumerate the equations. This is the first equation, and this is the second equation. First equation gives me x1 equals 2x2 minus 1. Right? So I just solved for x1 here. Then I can plug it into the second equation. So let's call this new equation maybe 3. Then 2 and 3 gives me this plus this equals this. I just substituted the more complicated expression for x1 that I received from equation 1 into equation 3.
Shouldn't it be plus 1? Oh wait, it's negative 1. Okay, never mind.
Okay. Yeah, that's a good point, by the way. So I'm going to be doing a lot of calculations in this course, but when you're somehow on the board and presenting things, sometimes you just like end up not being able to see the calculations, or when you're sort of starting to make a mistake. I'm going to try to not make a mistake, obviously, but it would be a good idea if you also did the calculations with me and verified. Okay? Very good. So we have this, and then what do? You just distribute the minus and so on. Let's do this, for instance. Minus 2x2 plus 1 plus 3x2 equals 3. At this point, I could have said, oh, this is the fourth equation and then the fifth equation, but let's not be that pedantic, perhaps. And then you consolidate things, right? So you say x2 and send the 1 to the other side is 2. Let's just call this equation, this is an equation after all, equation 4. And then what I can do is, of course, I can go back to equation 3 and plug in this value into this. To get the value for x1. Because you see, just because I solved for x2 and I was able to come up with a number, that doesn't mean that I'm done. In the system of equations, I have two unknowns. You're not done until you have values for everything. Now, that needs to be qualified a little bit because we're going to start talking about systems. We're going to look into systems that don't technically have numerical solutions like this, specific numerical solutions, but we're going to get there later. Okay, so x1 then equals 2 times 2 minus 1, which is 3. And so I was able to recover the value for x1 also. And now you're done. That's the solution. Any comments or questions about this? Okay. Now I'm taking the example of two equations with two unknowns, but I guarantee you the same methods essentially apply to more general equations. Now, here's a question. One of the important things in this class is going to be, well, you came up with some calculation. How can you verify or guarantee that this is indeed correct?
Plug both things back into equation 2.
Right, that's the point of this being the solution. When you say, oh, this is a solution, x1 equals 3, x2 equals 2 is a solution, literally is the same thing as saying, well, these are the values that satisfies this equation. So what you could do is, for instance, in the exam, whatever, if you want to guarantee, if you want to sort of convince yourself a little bit more that you didn't make any calculation errors, say check, plug in. So, 3 minus 2 times 2, what is this? This is minus 1. Okay, that matches. Okay, that's the first equation. Yeah. I just took the first equation here. Okay, and then minus 3 plus 3 times 2. What is this? 3, and that's the output I need also. So it works. Okay, so that's the solution. Good. Any comments or questions about this method? Now, certainly this is correct, and you're free to do this. But this is somewhat not very convenient, I would suggest. Part of it is, well, in this case, we had two equations and two unknowns. We could have we just started with one equation, and we could simply solve. Oh, go ahead.
Wouldn't this not work with anything that has more than two unknowns?
No, it would. It would. It would just take longer. Yeah. But yeah, that's what I'm getting at. It would work. It would work with more general equations, but it would be more cumbersome. And it would be harder to keep track of the variables and stuff. So in this case, we had two unknowns and two equations. We focused on the first equation. Now it's doable here because there's only another equation. But imagine having 5 equations and 7 unknowns. Okay. Well, you're going to solve, let's say, the first equation in terms of the first variable. You're going to take that, plug it into all the other equations to reduce the number of unknowns. Then you're going to keep doing this many, many times. Okay. I suggest to you, it's going to be cumbersome to write down. It is not impossible. It can be done. But we want to sort of like streamline this so that the thing scales. And the main reason I would suggest to you that this happens is because you're sort of like moving the variables too much. The method that really boils down to this matrix algebra business, reduced echelon form and stuff we're going to see later as well, is, well, keeping the variables where they are and sort of making adjustments on the coefficients somehow. So I'm going to erase this because this is not really the method that we're going to use, but I should check. Should I erase it or wait a couple more minutes? Technically, this is not the method you should be using, is the point anyway. So. So what's the idea for method 2? And this is the main method. And this is the main method, yeah. Keep the variables on one side always. I'm not going to switch to this notation yet. I'm still going to use this. Okay. The point is, I get to change the coefficients in the system if I'm careful about them. Careful about it, let's say. So for instance, one thing I can do is this. I could take this equation, this system, and I could perhaps scale the first equation by 2. Just going to multiply everything by 2. Just to give an idea. This equation is the same thing as 2x1 minus 4x2 equals minus 2. And then minus x1 plus 3x2. And if you want, maybe I'll just multiply this by minus, like so. And then I have a minus 3. I can do things like this. Does this make sense when I say, oh, this original equation is the same thing as this? What's the point? The point is, any solution to this is a solution to that, and vice versa. As long as you don't change the shape or nature of the solutions, you can reorganize the coefficients involved. Okay? And that's somehow is the more compatible way of thinking about how to solve equations, compatible with linear algebra. And so here's what I'm going to do. For instance, what I can do is this. This is another thing I get to do. I can take the first equation and add it to the second equation to get rid of x1 here. I'm going to keep the first equation, but then the second equation I'm going to replace by first equation plus the second equation. Here's what I mean. This. I'm going to write down every single step. Keep the first equation, but add one copy of this to this. what do I mean by this? Well, you just add the corresponding things. So there is no x1, and there's an x2 here. But I need to add the right-hand side also. When you're doing this, you have to add the whole thing. Does this make sense? I suggest to you and of course, we had found x2 to be 2 in the previous calculation, but forget about that for now. I suggest to you that this is, again, a system of equations, as you see, and this is equivalent to this system of equations. So maybe instead of this, maybe you want to write something like this. They're not technically equal, but they're equivalent. They're pretty much the same. Okay. So the name of the game is going to be to try to reduce the shape of the system as much as possible using these changes. And so just to be a little bit more explicit, let's also record what we actually did around this arrow. What did I do? I didn't do anything with the first equation, so I'm not going to write anything. I'm going to say R2, second row, replaced by R1 plus R2. So in a sense, this red thing is an operation that I applied to the system itself. Okay? Any comments or questions? Okay, let's keep going. For instance, what I can do next is, well, I can you see, I don't want to do this. I don't want to say x2 is 2, so I'm just going to plug it in and then solve. I don't want to do that. Okay, that would be more similar to method 1. Instead, what I'm going to do is I'm going to multiply the second row by 2, then add it to the first row to get rid of this minus 2x2. So now I keep the second row, and I add twice the second row to the first row to get rid of this. I don't see any x2 here, so now it's 3. And again, just to record what we actually did, this time we didn't do anything with the second row, so I'm not going to write it. But row 1 was replaced by row 1 plus 2, row 2. And of course, once you're there, that's the solution. Okay? Any comments or questions about this? Somehow, it turns out that this method ends up scaling much more nicer than this first method. And ultimately, the reason is this, okay? Somehow, this way of trying to solve equations end up being rather convenient, let's say, once you switch over to this. Okay? So this is the augmented matrix associated to this. So now let's try to write down the augmented matrices of these systems as well. You see, numbers are different now, so the matrices are going to be different. So this, like we wrote here, just use a different color. This turned into 1, minus 2, minus 1, minus 1, 3, 3. How about this? Again, the same idea, right? So 1 minus 2 minus 1. Same thing as the first row over here. And then here I see 0, 1, 2. And then here I have 1, 0, and then 3, 0, 1, 2. Does this kind of make sense, this conversion between the augmented matrix notation and the system notation? Yeah.
How did you get from that point to over there?
Oh, this was just like some arbitrary thing I did that I didn't actually use in the specific calculation. This is a valid thing to do, but probably it's not going to help me solve it. Right?
Then how did you automatically assume that x2 is equal to 2 over there?
I didn't assume it.
Well, we solved it earlier, but
Yes.
like, how would we
Applying
know
this,
that?
applying this gave me, it produced for me automatically that this should be the equation. Think about this. Take this, okay? How did I go from here to there?
Yeah.
All I did was I added this to this.
Okay, I see.
Okay? If I add this to this, well, x1s cancel out, and 3 gets reduced to 1. Of course, I chose doing this because I knew that this was going to happen in a sense. And this is where the sort of art of solving equations is going to come into play. But somehow, you just follow your heart. That's how I imagine it, at least. And machinery solves the system for you, in a sense. Yes?
I just want to ask, how does this tie into the m by n matrix?
I'll give another example in a second. Maybe you'll see there. Okay?
If we swap the first and second columns of all the matrices, would it be the same?
That's a good point. So your colleague is, I think, suggesting this. They say, well, this addition, I know, if I have something like this, I can flip these. It's the same thing also. You can do this, of course, but if you flip it like so, you would want to flip these like this as well, and that would, again, give you the same thing. That is something doable, but technically what we're doing right now is we're sort of using what are called row operations. So we're sort of biasing ourselves toward changing rows, but there's alternatively, you can also use like columns. We're going to see that later. Don't worry too much about it. But technically, yes, you could do that. Yes?
Is it notable that there's only one non-zero number in each row and column in that last matrix? Like, because that's technically the answers to both. So is that like the final matrix? Is that like a certain form?
In a sense, yes. Yes. Yeah, so we're going to slowly start sort of seeing significance in simple expressions like this. One of the best ones is this, 1, 0, 0, 1. When you have a 2 by 2, this is what is called the identity matrix, 2 by 2 identity matrix. Okay? So this is sort of the prime matrix that you want to get when you're trying to solve things. But there are sort of versions of this that are not as nice, but still nice enough. And these are what are called the reduced forms that we're going to see also. Any other questions or comments? So let me be explicit then. When we're doing this, what we're allowed to do technically. These are, it has 3 flavors. Okay? And we've actually seen 2 of them. The third one is kind of bizarre to state, but when it comes to matrices, it ends up being useful. So the first one is something like this, going from the original one to this, for instance. Scalar multiplication. I just scaled one of the equations by some number. It has to be non-zero, of course. Because when you think about it, if you were to scale something by 0, you're getting rid of the information. So you don't want to reduce the information there. So that's the first operation. Second operation is, well, adding some multiple, for instance here, of some row to some other row. That is allowed. That's the second elementary row operation. The third one is, it's kind of silly to say, but you also get to swap the number, the way the equations were written. In other words, instead of writing it like this, I could have swapped and written them like this as well. It doesn't matter in which order I write them. And this is what is called an interchange. So these are the 3 motions you get to do. I'll record them here. So 3, well, these are the only ones, so elementary row operations. One, scale. Okay, this means scale one row by some non-zero number. Scale a row by a non-zero number. That's the first operation you get to do, something like this. Second, what is this called in the text? Maybe addition or something? Replacement. That's called replacement in the textbook. Replace a row, let's say Ri, by Ri plus C, some constant, times Rj. Okay, so maybe let's write it as well. Row Ri by some non-zero number to get C times Ri. Okay, this is the second. And the third one, interchange. So change the positions. Maybe let's just write it like this. So somehow, this world of matrices, you want to imagine as sort of the world of computers, and you have to be like very precise as to where you're putting things down, where you're sort of storing your information and stuff, and you have to sort of be rather exact in the things you're doing. Comments, questions?
So that's R in the second one. That's Ri plus CRJ, right?
Yes.
So how does that make sense to like the first one you said, like scale a row Ri to get CRI? Where does the CRI come in?
Well, these are two different operations.
Okay.
Yes. So for instance, here, going from here to there, technically I applied scaling twice. I scaled the first row by 2, and I scaled the second row by -1. Okay?
It's like, why do you scale it differently? Is it just how it turns out, or?
It depends. So for instance, here I scaled it by 1, R2, or rather, I scaled R1 by 1 and then added it to R2. But here, I scaled R2 by 2 and added it to R1. So the scalar here was 2, here it was 1. How did I choose these numbers? Well, I'm looking at the system and I'm sort of engineering the numbers so that the variables sort of drop down. I'm sort of trying to cancel things out. Okay? Any other comments?
Wouldn't it make more sense to say the second elementary operation is just Ri plus Rj, since CRJ is actually just another version of elementary operation number
1? You could do it that way too, yeah. What your colleague is suggesting is, well, instead of thinking of it like this, I can just say, oh, I just first scaled. Oh, but the one point is that when you do this operation, you don't do anything in the jth row. So let's say that the jth row you want to keep fixed. Okay, you don't want to do anything with that. Yeah, very good. You can still sort of rewrite things multiple ways, but this is sort of the standard way of doing things. Later on, what's going to happen, of course, is that to each of these operations, 1, 2, 3, we're going to associate a certain matrix. We're going to define something called matrix multiplication, and it's going to turn out that applying these row operations really mean matrix multiplication. Okay, so everything is going to turn into this algebra with matrices in this class, surprisingly. And this is where sort of the beauty of linear algebra comes into play, because somehow linear algebra itself is linear algebraic. So when you're doing linear algebra, you're also doing linear algebra. Kind of bizarre to say, but so when you're doing calculus, it's not like that, for instance, exactly. But anyway, any other questions? I'd rather do another example, perhaps something more complicated. Let's do another example. Okay. So nice examples. Let me also check when we're finishing. Okay. And I'm always going to try to use this method, really. Let's keep this. Here's the example. Solve x1 minus 2x2 plus x3 equals 0. 2x2 minus 8x3 equals 8. 5x1 minus 5x3 equals 10. Okay, that's the aim. Again, what is our reflex? The first thing we want to record is number of equations, number of unknowns. This time it is 3 and 3. Okay? So instead of using this x1, x2, x3 in the second method, I'm going to switch over to the augmented matrix notation. Because as I kept applying these row operations, I actually didn't move x1, x2, x3 at all. So augmented matrix, I just look at the numbers, right? So I get rid of everything else. 1 minus 2, 1, 0, 0. You see, here I don't see x1. Whenever you don't see something, that means that the coefficient there is 0. Okay? 2 minus 8, 8. 5, 0, minus 5, 10. So go ahead.
Bottom left corner, is that a 3 or a 5?
This?
Yeah.
5.
5, okay.
Yes. Very good. So now I'm going to start doing row operations. Again, what is the point? I'll tell you what the point is. The point is, you see the bar? On the left-hand side, you want to see as many zeros as possible. Okay? And if possible, if something is not a 0, you want that to be a 1. That's the best thing you want to get. May fail, okay? Even though you're doing everything by the book, everything is correct, but we're going to get there later. Okay. So what can I do? These are what I can use, okay? The 3 operations. Well, for instance, I can take the second row and add it to the first row to get rid of this guy. Okay? Now, okay, so you have to bite the bullet here. Typically, once you fix something, something else is going to break. You're going to sort of have to change other things, but that's okay. So that's why, for instance, I'm not adding the first one to the other one, because I already have a 0 here. If I take this first row and add it to the second row, this 0 is going to turn into a 1. But I told you, zeros are better. Keep the zeros. Okay? So instead of adding first to the second, I'm going to add the second to the first. Okay. The third row, I'm not going to do anything, so I'm just going to record it as is. Second row, I'm not doing anything. I'll record it as is. But the first row, I'm going to update. I'm going to replace. Okay. So what is the operation I'm doing? Replace R1 by R1 plus R2. Okay. So that's 1, that's 0, that's -7, and then that's 8. Oh. Okay? So this is good. Somehow I got rid of this 0, but I'd rather have a 0 on the left-hand side. Okay? Having a 0 on the left-hand side is better. So I have one more 0 on the left-hand side. Okay. What else can we do? When I think about my next step, I'm trying to think of patterns. Oh, so for instance, one pattern I see is this. Oh, the second row is, it only has things that are even. I can scale everything by 1/2. Because 2 is better than, or 1 is better than 2. And you can sort of combine a couple of these operations as well. Similarly, I can scale the third row by 1/5. Because why? Because I'd rather, if I'm going to have a non-zero number, I'd rather have it be 1. Okay? So I'm not going to do anything with the first row. So record it. Second row, I'm going to scale by 1/2. Okay. Third row, I'm going to scale by 1/5. Okay. And so what do I get? 0, 1, -1, -1. Again, you have to apply the same thing throughout the row. You don't get to choose. If you're applying something, you have to apply it everywhere. Go ahead. Yeah, I wish it was -1, but yes, you're right, -4. Thank you. And then here I have 1, 0, -1, 2.
It should be plus 8 plus 4, 2 on the right-hand side.
0, 1, -4, 4. Not -4, right? Yeah.
Okay, apologies. Okay, and then this one is correct, I think. So this is better than this, you see. I have not more zeros, but at least I was able to reduce some of the non-zeros into ones. Go ahead.
Now, could we multiply the third row by like -1 and add it to the first row to get rid of all the ones?
So you're saying take this and basically get rid of this guy.
Yeah.
Yeah, you could do that, and let's do it, in fact. What your colleague is suggesting is, OK, I'm going to get rid of this guy. And how do I do it? I'll just take this and get rid of this using something. OK, I have 1 minute. So R1 replaced by R1 minus R3. I'm not going to write it because we're running out of time. I'm going to keep working on this on Friday. OK, but this is pretty much all there is to it when it comes to the first week. Thank you. OK, let's start. Good morning. Morning. So today we're going to keep working on examples. We're slightly behind schedule, but it's not a major issue. We need to talk about vectors and stuff like that, but we'll do that next week. Today I want to keep working on a couple of examples of how to solve systems of equations using these row operations and stuff like that. Before though, we go back into doing math, I wanted to mention that problem set 1 is up. Okay, so now if you go on Canvas under the assignments tab, if you go to the assignment assignment site for problem set 1, you're going to see a PDF file there. It's like this. I'm not going to distribute the printouts. I want you to perhaps have a look. Instead of going through every single thing, I'm going to let you look into it by yourselves. And maybe on Monday we can discuss just a little bit if there are any things that are somewhat confusing about the structure or the logistics of the problem set itself. One thing I want to say is that, each problem set I'm going to publish on a Friday, and it's going to be due next Friday. Okay. So you're going to have slightly more than 7 days to completely finish a problem set and submit your work. I would suggest that you start early. Okay. Instead of cramming it to the last day, start today. And by start, I mean at the very least have a look at what is needed. Things like this. Try to record which problems seem more complicated and so on. Because somehow, well, maybe I should ask you this. Okay, we have, let's say, 10, and then we have 20. Okay, there are two numbers. Which of the two is larger? Surprisingly, the other way around. When it comes to doing problem sets in this class, this typically means, okay, so a bunch of days you didn't do much, and then the last day you sort of spent all your time. You cram, okay? If you do this, this is approximately 0, in fact. You may be able to sort of get the grades for the problem set and so on, because I'm going to be rather lenient when I'm grading, but it's not going to be, so you're not going to be able to remember much of what you did. You're not going to understand really what you did and so on. Instead of this, do just a little bit every day. Okay? I know this is hard to manage. You have other classes and so on, but I guarantee you, if you leave it to the last day, you're going to end up spending more time. Okay? I promise you this. I'm promising you this. Do just a little bit every day. It's important that you have a look at a problem, sleep on it and so on, and somehow, even if you don't understand it, your brain understands it, okay? I am a big supporter or big believer in subconscious processes and stuff like that, and you would like to make use of that in this class. Okay. So let me just remind you what we were doing. We had an example. I'm going to write down the example, and I want to finish it. But just to reiterate, we have these 3 valid operations. These are called elementary row operations. Okay? They have 3 flavors. One of them is scaling. And when I write something like r sub I, typically I just read it as ri, of course, to be like fast. And when I write something like this here, you should imagine this lowercase I, which is a subscript, as something that runs from, let's say, 1 to m. So as you're changing I, you're iterating over each of the rows. This is fairly common notation. So some people would write, oh, for each I from 1 to m, blah, blah, blah. But let's be somewhat faster. And when I draw this arrow, I really mean replace ri by c times ri. Many of you are doing computer science, and in certain languages you would see something like this. Instead of writing this, you would see ri equals cri. Of course, you don't really mean this is equal to this. You're saying I'm replacing this by this thing. But we're doing math, and this kind of gets confusing. We're not going to do that. We're not going to use this notation. I'm just going to use this arrow notation. That's the first. Second flavor is replace. I'm replacing the ith row by the ith row plus some constant times some other row. Okay, that's replacing. And the point here, one of your colleagues was, so we had discussed this last time, in this replacement, you're doing something to the ith row, and you're not doing anything to the jth row. Okay? And then the third one is what is called interchange. When it comes to systems of equations, this seems like something silly to do. You're just like rewriting so that the first equation now is the third equation and so on. But somehow when you switch everything to matrix language, this ends up being an important thing. Later on, we're going to start talking about something called permutation matrices. And perhaps more generally, we're going to talk about something called orthogonal matrices. So that's going to sort of evolve into that later. And let me add a couple more phrases from the textbook. Technically, applying these elementary row operations one after another to get as many zeros, so to simplify the system as much as possible, is what is called row reduction. And you might also see the phrase Gaussian elimination. Okay, these are pretty much the same thing. Now, one thing that you're going to need that we might not be able to cover today, you're going to need in the first problem set is what is called echelon forms. And essentially, an echelon form is going to be a systematized sort of classification of these simplest matrices. Okay, we're going to talk about a certain shape, certain pattern, and so on. We're going to get there. But that's what we have so far. Any comments or questions? Go ahead.
Does the bottom, or does that sentence say, get as many zeros as possible on the L plus fifth?
Oh, okay, that's a good point. So that's an abbreviation I'm going to use very often. LHS means left-hand side.
Oh.
Okay. There's also RHS, right-hand side. Okay. Good point.
When you release the homework, do we have all the knowledge that we need to complete the homework by Friday?
Like I said, I hope so, but so for instance, we may not be able to reach to the echelon forms exactly. So I'm going to do my best, to say the least.
If we don't reach that, are we still required?
Yes.
Okay.
Yes. Certainly you can work on the other problems over the weekend.
Yeah.
So yeah, I will try to synchronize the problem sets to the topics that we're discussing in class, but I don't quite know the types of things that we're going to talk about. Maybe certain things are not super clear to you guys, or maybe I'm sort of not doing a good job and then there are many questions and stuff like that. That means that we're going to sort of slow down a little bit. But that is the cost, unfortunately. Any other comments or questions? Okay, so here's the example that we were looking into. And again, let me write down the system also. At this point, I hope it is clear that the system notation is just a notation, and you might as well just switch over to matrices and stuff like that. And you don't technically need to write down the systems themselves. You can just switch over to the augmented matrix notation. But still, for now, let's write the equation, or system of equations. Like this. Equals 0. Then I have 2x2 minus 8x3 equals 8, 5x1, and then minus 5x3 equals 10. And what is the task? The task is to solve for x1, x2, x3. So solve. Immediately we switch over to the augmented matrix notation. Okay, let me do that again. Maybe I'll write it here. What do? I just look at all of these numbers. I get rid of variables. I get rid of equalities, and I put them basically in the same format into an array of numbers. And just signify that here there's an equality, I put a bar. In the textbook, they don't do this. It's not really that important if you do it or not. I like doing it. You can just choose which one works better for you. Okay, that's my augmented matrix associated to this equation. And so let me try to remember what we did before. What did we do? We took this, the second row, and added it to the first row. In other words, we apply this replace operation. Why did we do this? Well, because we said, oh, there's a 2 here and there's a minus 2 here. If I take this second row and add it to the first row, I'm going to be able to get rid of this minus 2. Other things are going to break down, but that's not a major issue, okay? If I'm able to get to 0, that's a good thing for me. And so let's write it. So R1 is replaced by R1 plus R2. And consequently, I get this new matrix. 5, 0, minus 5, and then 10, 0, 2, minus 8, 8, 1, 0, because I'm adding the 2. Now that's a minus 7. And finally, it's 8. I always have an issue with writing out this specific 8. OK. Then what else did we do? I think we did scale twice in one go. We scaled the second row by 1/2. Why? Because 1s are better than 2s. Okay, I want to simplify as much as possible. And again, the third row, instead of scaling by 1/2, we scaled by 1/5. Again, why? I look at this guy. I want to get rid of this and turn it into a 1. At least at first glance. Again, let's write it. So what did I say? R2 replaced by 1/2 R2, and then R3 replaced by 1/5 times R3. And the end result is this. First row, I didn't do anything, so I'm just going to record it. Now this is going to turn into 0, 1, minus 4, 4. And now this becomes 1, 0, minus 1, 2. Okay. Well, let me also reiterate, technically you don't need to write these down, what specific row operations you're doing, but I would highly recommend that you at least initially record what it is that you want to do, like so. Eventually we're just going to sort of, in fact, eyeball sort of these row operations. You're going to say, oh, this cancels out, that cancels out, whatever, blah, blah, blah. When it comes to sort of more complicated things, more sort of high-level structures that we're going to discuss, we're just going to sort of basically eyeball the shape of the matrix later. But for now, I think it would be good to take it slow and do things step by step. And now, I think one of your colleagues suggested, well, I can get rid of this guy, and I can take the third row and subtract it from the first row. Right, so R1 replaced by R1 minus R3. Again, let's write it. And what's the method I'm using? I look at the specific row I'm doing something on or something for, and then the other ones I immediately record, okay? Because these are just going to sort of stay as they are. And then now I have a 0 here, 0 here. Now I need to subtract from minus 7, minus 1. So that's the minus 6. Okay, and then that's a 6. Is this correct? Okay, let's keep going. So what else can we do? For instance, the first row I can scale by minus 1/6. Why? Because again, I'd rather have a 1 instead of a minus 6. Let me just write it here. Or maybe I'll write it here, actually. So we're going to go this way now. Replace R1 by minus 1 over 6 times R1. And ultimately, you get this. Okay. Can we keep going? Yes, for sure we can go. We can keep going. For instance, I can take this one and start using it to knock out these two guys. Okay. So for instance, what I can do is, I'm not going to write down the row operation. I'm going to leave that to you, in fact, this time. So I need 4 times this to get rid of this guy, which means if I multiply this by 4 and add it to this, I get a 0 here. This plus this is 0. This plus this is 1. Okay. And the exercise is to write down the row operations. Okay. Which row operations did I use? Okay. Go ahead.
Or are you like asking it?
Yeah, do it on your own. Yeah. Okay. So now, for instance, here, even though technically this is as far as I can go, okay, here, okay, so this is the left-hand side, and I have a bunch of zeros, and let me perhaps ask you, would you agree with me if I were to say, well, I can't make this any better. I cannot generate more zeros here using row operations only. Right? Because, for instance, imagine trying to get rid of this one. You don't have anything else left. That is, you're stuck here. This is going to stay. Okay? And likewise, you cannot get rid of this one over here. You don't get to use this to get rid of this. You can only use this entry or this entry to do something about this. So you're done. You're stuck there. And again, here, you cannot do anything about this. Does this make sense? So this is based on my sort of general description as far as you can go. And technically, at this stage, you can cache out. And we have the solution, really. But it's going to be better to go one step further using this interchange so that you have what I would like to call a staircase symbol. And here's what I mean. What I want to do is I want to replace, I want to interchange the first and the third rows so that I'm seeing a staircase like this. Okay. So now I'm going to say R1 interchange R3. Middle one stays as is. Now I see 1, 0, 0, 1, and then here 0, 0, 1, minus 1. And here's what I mean by the staircase. Okay? So for instance, the first non-zero entry in the first row, I want to be to the as far left as possible. And the first non-zero entry of the second row, I want to be later. Okay? And then the third, I want to be later than the second, like so. I want to see something like this. Underneath, I want all zeros. Okay? That's what I want all the time. In other situations, these may end up being non-zero. That's going to be less of a problem. In fact, that's going to be not a problem. But you really want to have zeros here. Okay. So this now is what we're going to say is in reduced echelon form. Let me just introduce the phrase. And let's also mention what I really mean when I say, oh, you can cache out at this point, or cache in, I guess. Cache in, cache out, it doesn't matter. Meaning, ultimately, when they're asking you to solve something like this, they want values for x1, x2, x3. But that's just a matrix. So once you do these calculations, I want something like x1 is this, whatever. And how do you do it? Well, you remember the whole point of using this augmented matrix is that you keep where the variables are. At each of these steps, if I wanted, I could have transitioned over into the system notation. In particular, if I, for instance, transition at this stage, this literally tells me x1 is 1, x2 is 0, x3 is minus 1. Go ahead.
Why don't x1 and x3 swap when you do the interchange?
Because interchange, in terms of equations, literally corresponds to writing the third equation instead of the first, and then the first equation instead of the third. That's a very good question. Does that make sense? Okay. So once you're at this final stage, you've gone as far as you can go. On the left-hand side, it's as simple as possible. Now you cash out, okay? So 1, 0, minus 1. Let me just check that I haven't made any calculation errors. Okay, yes, seems correct. Go ahead.
So you mentioned that it's not necessary that those are zeros on the right side. Do they have to be ones going down the diagonal?
That's also not technically necessary. But this, okay, so echelon form is something more general. Then you have this more pristine situation, that's called the reduced echelon. I'm going to mention what that exactly means later. Okay? I'm just introducing the terminology for now. Any other questions?
Just to be clear on that.
Yes.
Reduced echelon form, is that, will there be ones and zeros only?
There will be as many ones and zeros as possible.
Okay, yes, but each row would only have one, and the rest would be.
Not necessarily. Not necessarily.
Even in reduced echelon form.
Yes. Underneath, you would have always zeros. Sometimes you're going to have non-zeros here. Okay. You'll see more examples, okay? Any other questions? I want to keep solving examples. Where's the one that I liked? No, I want this one. Here's another example, okay? New system, same issue. Solve something. Solve an equation. Again, all you're allowed to use are these elementary row operations. Again, first we're going to switch over to the row augmented matrix, and then we're going to start doing elementary row operations like this. Okay, erase all this. Let me erase this as well. Do it from scratch. Here's the example. Solve now this one. x2 minus 4x3 equals 8. 2x1 minus 3x2 plus 2x3 is 1. And then 4x1 minus 8x2 plus 12x3 equals 1. Immediately, okay, I go and switch over to the augmented matrix. And again, let's also remind ourselves, when we see a system like this, we also make a mental note of the number of unknowns and number of equations. Again, this time it's 3, 3. I'm not going to write that. Okay, so. Four minus 8, 12, 1. Okay. Now, for instance, maybe I should ask you, what could be the first move? There are many options, by the way. There is no sort of unique way of doing things. Go ahead.
You can swap the first and third rows.
You could, but I would suggest leave the swapping to the last moment, okay? Because you're just going to, waste space and just sort of beautifying what is written.
Okay. It might not help as much as it did before, but we could divide the last row by 4.
You could do that too, but then there's a 1. I'd rather keep it with integers. Now, technically, you can put rational numbers, complex numbers. You can put, in fact, matrices as these entries, which we're going to do later. But if these are sort of like integer value, then typically these are the types of matrices you're going to see, because I don't want to sort of, this is not supposed to be torture, and you're going to do these things by hand. And so instead of trying to divide this by 4, which is valid, it's something doable, I don't like 1 over 4. I'd rather keep that one. Yeah, go ahead.
I would do replace row 3 with row 3 minus 2 row 2.
Minus 2 row 2, because you want to get rid of this. You can do that. What else? So, okay, before going into that, do we all see what your colleague is suggesting?
Yeah.
Your colleague suggests, oh, there's a 4 here, and I want to knock that out. Okay, that's possible.
I was kind of just going to separate that into multiple steps. I was just going to double the second row.
Oh yeah, first you're saying, let's first double the second row and then perhaps add it or subtract it from this one.
Yeah.
You can do that too, yes. Any other perhaps first guesses?
You could also replace the third row with the third row plus 2 times or 3 times the first row.
Third.
Get rid of the last element of the third row.
Oh, you want to sort of use this to knock out this? These are all possible things to do, okay? Now, I have something else that I had in mind. And this is one of the reasons why ones are better. Ones are sort of like jokers, okay? They are more powerful. If I use this, I'll be able to get rid of both of these rather easily. That's what I want to use. I want to take this, add 3 times the first row into this to get rid of this guy. Does this make sense? All of the things that you suggested also work, okay? They're not wrong. It might take longer and stuff like that. And how do you figure out which one is better? Well, that's sort of like, that's the art of it, okay? You at this point, you have to just keep experimenting. So I'm going to take this one and get rid of these guys. Because for instance, instead of using this to get rid of this, I see, oh, if I try to use this to get rid of this, this is still going to stay. So if I can get rid of these guys before, my job would be easier. Does this make sense? Again, how did I figure this out? I'm just like having a look at it and stuff like that, and sort of. This is something you gain by experiment. So 0, 1, 4, and then minus 8. And by the way, this is also where using a computer is not going to help you. Like a computer easily will be able to reduce this, okay? But the way computers reduce matrices like this is very different. And just by using a computer, you'll be able to come up with the answer. And in fact, in the first problem set, there's a problem where I'm asking you, take this matrix, put it into Wolfram Alpha. It's going to tell you a bunch of things. Just record these. You're going to at least have sort of some sense as to, oh, how things are and like what are important things according to Wolfram. But somehow trying to do these things by hand and trying to optimize the procedure so that you can do them is going to help you understand the underlying structure. Okay? So I'm taking this, I'm going to use it to knock out these two guys. To be specific, what I'm saying is replace R2 by R2 plus 3 R1. And then R3 by R3 plus 8 R1. Another reason why I'm sort of focusing on using R1 first is, first of all, I told you that's a joker, that's a good one. And also it has more zeros too. That means it's going to be less costly to use R1. You're going to have to compute less stuff. Okay? So zeros are sort of like a double-edged sword, is what I'm trying to say. If you're beginning with lots of zeros, that means when you're doing row reduction, that's not going to change too many things. But if you're toward the end, that means if you have too many zeros, you're not going to be able to get rid of things. That's why it's a double-edged sword. OK, so let's write this down. You see, this guy, I don't need to compute anything. I know that this is going to be 2 and 4 immediately, because this is a 0. OK? So now that's a 0, that's a 0 also. So now I need to compute these 4 numbers. Again, I might end up making a calculation error, but still. So 3 times this is minus 12, plus 2 is minus 10. 3 times this is 24, plus that, 25. OK? And then this, right? So I'm multiplying this by 8, and there's a minus here, don't forget. So minus here. 8 minus 32 plus 12 minus 20. 8 times 8, 64 minus 1, or plus 1 rather, 65. OK? Is this correct? Now, I got used to doing these calculations because I've been teaching this class for quite a while. If you're having issues with doing these calculations without writing them down, there's no shame in actually writing things down, OK? On the side, you can say, oh, I'm going to do this. And it's like 0, 1, minus 4, and then 8. And then, let's say, what did we do? We multiplied it by 3. You can say something like this, perhaps. This is now 0, 3 minus 12, and then 24. OK? You can sort of like write it on the side and then erase it if you want and stuff like that. There's no shame in doing this. OK? Comments? Yeah.
So we have 2 parallel lines here.
What do you mean?
Rows 2 and 3 are parallel.
Oh, yeah, OK. Let's not go there for now. Your colleague is suggesting these I can visualize using geometric language. That we're going to start doing next week. For now, I just want to think about solving. OK? So what else can I do? So you see, slowing this, or not focusing on the first column kind of helped out, because now there's like some proportionality. Once you try to get rid of this, you're also going to get rid of this, for instance. Do we see this? I guess that's what you meant. That's what you meant. Yeah. So your colleague is suggesting, well, don't think about the right-hand side. This is like 2, 0, minus 10. And if I multiply it by 2, I'm going to be able to knock out both this and this. OK? And so let's use that. Replace R3 by R3 minus 2R2. I'm not doing anything with the first row. And likewise with the second row. And again, if I wanted, I could have just scaled this by 1/2. But then I'm going to have a 25 by 2 here. I'd rather not worry about these rational numbers here. Okay. And so here I'm going to have 0, 0, 0. And here I'm going to have something that is not 0. Okay. You don't technically need to compute it. But let's try to compute this. What is this entry? Multiplied it by 2, 50, subtract 15. Question?
It just clicked.
Okay. Now at this stage, we're done, actually. Could anyone sort of justify why we're done?
Doesn't this not work? Because that means that the last row would mean that 0 times all 3 unknowns equals 15, which doesn't make sense.
Okay. Any other comments?
This means that there's no solution to the system of equations?
That's another way of saying the same thing. Any other comments?
Wait, how did you realize that?
Okay. So this is the rule, okay? When you have an augmented matrix, if on the left-hand side you zeroed out, but on the right-hand side you don't see a 0, that's a bust. That means that there is no solution.
Which side on the right side?
This is 15. These are all zeros.
Okay.
Okay. Why is that?
So if the whole row has to be 0 in order for it to not work?
What do you mean by not work?
Like the 3 zeros on the bottom.
Yes. Yes, you have to zero out the whole thing.
And it doesn't matter which, like.
No. If you can get 1, that means that you're busted.
Okay.
Meaning, so why is that? I'm just going to look into this, okay? When I switch over to the system notation, just give me a second. When I switch over to the system notation, this third row is going to say 0 times x1 plus 0 times x2 plus 0 times x3 equals 15. But I don't care what x1, x2, x3 are. Left-hand side is going to be 0. So you did some stuff and you obtained 0 equals 15. That cannot happen. If you get something like this, assuming that you made every single thing correct, so every single step is correct, that means that there is no solution. So okay. No solution. This can happen. You were asking something? Okay.
Couldn't you say that it also doesn't work because, like, in the previous one, the second and third rows have like the same left-hand side but different right-hand?
You mean proportional left-hand side, but not proportional right-hand side.
Yes.
Essentially, you can say the same thing. So what your colleague is suggesting is that, well, even before going to this step, I see that, oh, the left-hand side is proportional, but not the right-hand side. Technically, when you have this, that means that it's going to lead to something like this. And if you wanted, you could have deduced from that too, there's no solution. Okay? But the point of this augmented matrix business and the elementary row operation business is that even if you don't have these insights, you keep running the thing, and eventually you're going to get something. Okay? And you're just going to be able to read off the numbers, and it's going to tell you.
If the left-hand side and the right-hand side were both the same,
Then you're still in game. You're still playing.
would that be, I would think that would be algebra numbers, right? Something like that?
What do you mean?
Like if,
We'll get there later. Okay. So let me just translate perhaps what your colleague is suggesting. If I had seen here a 0 as well, meaning the whole row was 0, then you're still in game. Okay? That doesn't mean there's no solution at that point. No solution happens if on the left-hand side you have all zeros, on the right-hand side you have a non-zero thing.
How would you figure out what the unknowns are in that situation or equals 0? Because wouldn't anything work?
We'll get there later. Okay. Instead of going into because the thing is that, like, if I try to answer questions like that, it sounds like philosophy. Okay. I'd rather try to do an example and we'll see sort of one out in the wild, and then we'll figure out what to do then. Technically, if you see that, that means that one of the equations in your system doesn't give you any information. You have less information than you thought you had. We'll talk about all that later. Any other questions about this specific example? Okay. So now I'm going to introduce a terminology. For a system of equations, I'm going to say the system is consistent if it has at least one solution. And I'm going to call it inconsistent if it has no solutions. Okay? So this is an inconsistent system. So in the textbook, you're going to see determine if this is consistent. This is sort of like a leading way of asking the same thing. I like just saying solve. Okay? So I'll write it here. Write it here. Just check the time. Okay. Yep. So definition. System of linear equations is either consistent or inconsistent. So no solution, at least one solution. Okay. This case is when you call the system inconsistent. That's what that means. When you say a system is inconsistent, you really mean it has no solution. Consistent. Here you call it consistent. Okay. Now, just because you have one solution doesn't technically mean that you have exactly one solution. Okay. This technically means existence. But once you have existence, you want to talk about uniqueness also. And there we bifurcate also. We say in this option, either you have exactly one solution or you have infinitely many solutions. We haven't seen an example of a system that has infinitely many solutions, but hopefully in a second I'll write down one. Okay. Infinitely many solutions. And that's a bizarre thing, by the way. Somehow you don't have anything in between. You don't have a linear system that has 5 solutions exactly. In particular, that means if you sort of chase the logic, if a system has at least 2 distinct solutions, in fact, it has infinitely many solutions. This has to do with the nature of the numbers that we're using. We're using real numbers. There are other sort of situations where perhaps you use binary numbers and stuff like that. There, the thing changes. But for us, this is the case. And this, of course, the sideways 8 means infinity. Okay. Any comments or questions so far? Now, later on, we're going to try to really say more about this infinity. Okay? And this is where the geometric language is going to come into play, because somehow if you think about a line, a line consists of infinitely many points, but so does a plane. But clearly one of them is a larger infinity. Okay, a plane is larger. The technical way of saying is that the plane has more dimensions than a line. We're going to get there later. Okay. Any comments or questions? Let me see. I think the next example I have in mind is going to take some time. So I'm going to give toy examples for each of these cases. And I'm going to use systems of two equations with two unknowns, okay? Because the point is, when it comes to two equations with two unknowns, I can visualize it as two lines on the plane, okay? And so I can actually associate certain graphs or caricatures to each of these cases. So for instance, if I had a system corresponding to two parallel lines, like your colleague was suggesting, that would be the case of no solution. Exactly one solution would be a crossing, whereas having infinitely many solutions would correspond to the case of having both lines sort of coincide with each other. So maybe I can draw it like this. Apologies for the caricature, but that kind of represents two lines being the same. If I wanted to actually write down equations, let's perhaps write it like this. No, at least one, exactly one, infinitely many. These are the three options. For instance, for this one, I can imagine something like this. X plus y equals 1, x plus y equals 2. That's a valid system of equations. This has no solution. Okay? This is, for instance, x plus y equals 1, x minus y equals 1. This is exactly one solution. Infinitely many, x plus y equals 1, 2x plus 2y equals 2. It's kind of silly to write these down, but these are valid things. And a good exercise now would be to verify that indeed these all fit into the corresponding paradigms. Okay. And here's a trick that I'm going to leave you with. You look at this crisscross, okay, this by this, minus this by this. In this case, for instance, this is minus 1, that gives you minus 2. Whenever this crisscross is not 0, that means you have a unique solution, at least in the case of 2 by 2s. We're going to call that determinant later. Okay, that's it for this week. Have a nice weekend, and I'll see you on Monday.